Okay, so welcome back. So this is a real big marathon here, right? So Sangeeta just told me it's now 1 hour and 2 hours, and only then the tea break comes. That's long. Yes.
So take a slow breath.
Yeah. So let's see. So now, since we now know everything about radicals, so let's talk a little bit about photoredox chemistry. And so there will be essentially two parts. The one part today is photoredox, and then there will be tomorrow something a little bit about energy transfer, which I will combine also with something I like to call uphill catalysis. And so let's look at this. So now we talk a little bit about photoredox and photochemistry. I think we touched on this before. So why did it become so popular in the last 15 years? I would say this is pretty much a very spectacular publication by David McMillan, and I'm going to show this to you. That was 2008, so that would be 17 years actually now, which really showed in a very spectacular way what you can achieve with photocatalysis in a way which you could not have achieved before. But the big question is, why now? Why not much earlier? And I think I showed you already a few slides today that that a lot of photochemistry and also a lot of the principles were already available and known in the 70s and 80s, and that was really fantastic work which was already done there. Yeah, so I think quite a number of good answers here. High temperature can be replaced by room temperature processes. This is probably pretty much true, but this is something you could have done 50 years earlier as well, right? That is probably not why it suddenly became so popular. Climate change, the sun is shining more these days. How many photoreactions, if you have already ran any, do you run outside, where you go with your flask outside in the sun and then you see, let's see if it is working. I think reactions you can do under sunlight irradiation, it's typically which we would understand visible light irradiation, but in a way, there might be processes which might be valuable to do indeed outside, but typically when we run reactions in the lab, we want to have reproducible conditions, right? And if you do a reaction in indoor under sunlight, that might be very different from doing a reaction in Regensburg, Germany under sunlight, right? The intensity is different. Maybe even the window of the wavelengths, and one day it might be hazy, one day it might not be hazy. So in terms, and we like, of course, when we develop photochemistry, we like, of course, having reproducible processes. And this is already hard enough, and we'll go into this a little bit. This is already hard enough when you do photochemistry in the lab, because even there, results might be very different, and it depends on the lights, it depends on the reactor. But maybe even you have seen that with the same lamp, a month later your result is suddenly different. So reproducibility is a pretty big issue which one has to master, right? Indeed, low-cost LED became available. I think that is indeed the major driving force. I told you already when I did photochemistry during my PhD, if I wanted to run this overnight, we had these very big hot lamps. We had to stay with them during the night. They were very expensive. And so to do photocatalysis these days with LEDs is really quite nice. Efficient photocatalysts were developed. That is in a way true. But if you look at one of the photocatalyst, and I will show this to you in a moment, and you probably are all aware of this, ruthenium Bipi-2, that is known since the 70s. And so that is really, there might be some different ones, some iridium photocatalysts, as you will see here in this lecture. I believe in copper and iron, but I think there are also pretty good ones around. It abides the principles of green chemistry. This is also an interesting statement. In a way, yes, because of course light is clean, and if you can do reactions then by light, you have the feeling that it is very green. But I think it's more the question, is the process cleaner? Do you make less byproducts? And that might be the case, but might not be the case. The one interesting thing for me, which I learned from our industrial partners, is that at least in considering the energy you're using, compared to a reaction you have to heat, and let's say even heat it at 100 degrees, it's not so clear that the energy that a light reaction by an LED is more efficient, because that LED needs a lot of electric power. And very often, if you look at the reactions which we are running this 24 hours and sometimes even longer, right? And typically, one of the first considerations often in industry is that they ask, can we replace maybe the light step? And they like the light step, especially for screening, you can get a broader scope. But then if it comes to the question, can we produce it on kilogram scale, the energy balance is not so good as we all have this gut feeling that we say, oh, we just switch the light on, right? And we do this every day. We're switching on lights in our houses, and now actually also with the new LEDs and the new energy saving lamps, it doesn't become so hot any longer, the lamps. So the energy efficiency has become a lot better, but it might not be so good as it might seem. Okay, so lots of aspects to discuss here. But of course, if you look at this, it looks like it not looks like, it is really ideal from many points of view, right? It provides energy, clean energy, if the electricity can come from renewable resources to drive the reaction. I think one of the very big issues, again, compared to 30, 40 years ago, is that the LEDs are very selective. You can choose a given wavelength, and you're not going in with like the whole range, for example, which you would have from the sunlight, right? From the sunlight, we have some UV, we have then a broad range of visible wavelengths, but indeed, we can, with the modern LEDs, we can tune the wavelengths in very narrow regions. Right? Can be used in excess and leaves no trace. That's why I say the energy efficiency is sometimes not so great, because we use it in large excess. And if sometimes quantum yields are very, very low. And so, yes. And so from a point of, it's a large excess, usually when we use in large excess in the reaction, then we have of reagents, then we have to do a big cleanup. But here, of course, we don't have the cleanup. So the excess from a point of running a reaction in a clean way is good, but of course from the energy balance it might not be. Easy to generate, and we always felt that in the beginning this applies to visible light, because when the LEDs came out, the typical LEDs we would have were 530 and 400 nanometers. But now it becomes a lot broader, and so suddenly we have LEDs at 400 nanometers, 365, and even harder UV is available. They become progressively more expensive, but nevertheless, if the reaction, in many reactions we run now is at 365 or so borderline, that's not visible light any longer, but if then the reactions work because you can excite the molecule or your catalyst in a better way, then this is very much acceptable. So I think this is something I feel which is changing. In the beginning, 15 years ago, we were all very happy about this idea that we can use visible light. I think we are expanding now also to the UV region, and again, it becomes with the availability of the UV lamps, right? Safe and not toxic, that's always what is being said, and the question is that really true? And the answer is pretty much no. So the one thing I heavily urge you, if you have ever run a photoreaction, you need, even with visible light, you need to make sure that you're not looking into these high-powered LEDs, because it will harm your eyes. Maybe not as fast as a UV lamp would do this, but it is definitely, and we do this in our lab, and I think you do this too. We are shielding our hoods. We're really making sure, or we put the lamp in the reactors, which we can close. We really make sure that we're not getting exposed to the light, because that is high energy and high intensity. Right? And so this is maybe a little bit the outcome. Just a few photophysical principles. What is it? What we are typically doing is we have a molecule in the ground state, and then upon light irradiation, we bring it to the excited state. And there are a few principles which I think we can maybe probably disregard if you just run reactions, but it's interesting to know. There's something like the Franck-Conant principle, and this tells you that if you bring a molecule in the excited state, the geometry is not really changing, so it stays the same. And so in this type of representation, which I've given you here, if we say this is on the horizontal, is the nuclear coordinates, the excited state which will be reached will not change the positions of the atoms or so. So it might not go to the lowest excited state, but it will reach an excited state which is simply from the geometry of the molecule the same. And then Kasha's rule, also very important, says that you might, with your excitation, you might reach different excited states, which I show here with S1, S2, S3. So you not necessarily will go to the lowest state, but if you reach a higher state, the vibrational relaxation to the lowest excited state is incredibly fast. So any type of chemistry which we consider from the lowest excited state. That is really what Kasha rule is saying, and this is why it works. So we do not need to be concerned about different levels of excited states. We get the chemistry of the lowest excited state. Okay. And then typically what we do is we have the molecule in the excited state. It's in the so-called singlet state, but the singlet states are very, very short-lived, too short-lived to do chemistry. And so what has to happen is that there needs to be a spin reversal, so-called intersystem crossing, and that can occur quite easily. And then you have the so-called triplet state, and the triplet state is the one we get the chemistry out of this, because that is much longer lived, and until it goes back to the ground state, thereby it emits light. That's what we call phosphorescence, and this is the important process which we have, right? And so again, if you look at the photophysical processes, the absorption is very, very fast. 10 to the minus 15 seconds is given here. Then the relaxation from any type of excited state to the lowest excited state, you see here it's also very fast. So that's the idea of Kasha's rule, right? Even if you're in a higher excited state, you go back to the lowest excited state. And then very important, the excited state lifetimes. And you see here the excited state lifetime. Let me switch on the laser pointer. The excited state lifetime of a singlet is much, much shorter than the excited state lifetime of a triplet. And so that's where we rely on this intersystem crossing, which is typically also very fast. And then the active chemistry, which we can get out, is the excited triplet state. And so the excited triplet state is lower in energy than the first singlet state. So we're losing a little bit. So not all the energy we can use to go to the first singlet state can be actually be the one which we are going to use. Okay. And then, of course, organic chemistry do not absorb light. And you see here a number of typically organic compounds. and they all absorb in the UV region. And maybe if you're lucky, carbonyl compounds, alpha beta unsaturated ketones, once they get a longer pi system, they might go around 330 or so nanometers, but that is still UV range, right? And only nature, of course, has done it. If you have something like these vitamin A, these rhodopsin molecules, which have very long extended pi systems, they absorb in the visible light, and this is the reason why we can see, right? But most of the organic compounds we consider will not absorb light in the lower in the higher wavelength region, and especially not in the visible light range. And we all know that many of our starting materials are transparent, right? And only if we do a reaction, only if something goes wrong, then they turn black. But this probably has other reasons, right? You might precipitate small particles or whatever. And so that is the reason why we are using photocatalysts, right? Because we are using a photocatalyst which can absorb in the visible range, and then that photocatalyst can do two things. It can either transfer electrons to our substrates or can transfer energy to the substrates. And these are the two processes which we would like to look at. And so in this first lecture today, I will cover photoredox catalysis and also show applications, and also the tutorial we would like to do later will be out of this. And tomorrow there will be a section on energy transfer, and that is also, I think, in many aspects very excited, especially since it allows you to drive reactions which are thermodynamically unfavorable. Photochemistry is actually even older than 50 years. There's this famous, and maybe you have seen that picture, famous Italian chemist, Giacomo Giamicciani. He already in the beginning of the 20th century, this is a picture from his laboratory in 1912. And of course, Italy is a country, at least in Europe, where the sun is shining, maybe still not as much as in your country, but it is a pretty good place probably to do photochemistry. And you see, this is pretty nice, right? What he did. It's like he has put on the balcony, he has put all types of flasks and so on. And so he was studying how molecules can interact with light. And he also had an amazing vision. In this science publications, he writes that he thinks that one day all our buildings will have glass windows, and so the sun can shine in and drive reactions, and we do not need conventional reactors any longer. So really a visionary in this aspect. And I often wonder what would happen if he would now, you see, he died 1922, we would be alive 100 years later to see how his vision, maybe with the glass windows and in the buildings, is not a reality yet, but how photochemistry has developed. Okay, so again, if you look at the wavelength spectrum of the sun, that is very, 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 very broad, and therefore the LEDs give you a very nice way to have very distinct absorptions in the wavelengths. One thing to consider is you need to see how much energy is actually in these photons. And even in a blue photon, so we have an absorption at 440 nanometers, it's only 270 kJ per mole. So I gave the kJ this time. So now we have, at least in my head, I have to divide by roughly 4 and a little, so that's like 65 kcal or so. That is not really sufficient to cleave strong bonds. So CC bonds, CH bonds is completely out of reach. That might cleave something like a carbon halogen or a carbon sulfur bond. And then if you go down to green light or red light, you see you're getting weaker and weaker bonds. So the direct bond cleavage is one thing which is which you would need higher energy light. And that's one of the reasons why we now see with the LEDs, having LEDs at 465 nanometers and so on, that we might go into this region where we can do this, but then also it becomes less reactive. And therefore the other opportunity is, and we will see this, is that we can do the catalyst, the blue photon can excite a catalyst, and then we can do energy electron transfer to trigger reactions in a different way. Okay, so we talked already, we don't need to answer this. Is sunlight a good light for photochemistry? Probably not, because you would have a region and months dependent yield if you run the reaction, so that is probably not such a good idea. So let's look at one of the most famous photocatalysts, and that is ruthenium bipi. And so the typical thing what you do is you bring the ruthenium bipi in an excited state, and then in this excited state it can actually do two things. And so I've shown you the one process here. This is the metal to ligand charge transfer. It can actually transfer an electron from the metal center to the ligand. This is what we call metal to ligand transfer. So in that moment it gets oxidized. So the metal is now ruthenium-3, and that is a strong oxidant, stronger than in the ground state the ruthenium-2. But then on the other hand, your ligand has become a radical anion. So that is now suddenly a strong reductant. And so that is the one thing which is also interesting to know. Maybe I think you all know already a lot about photocatalysis, but that is maybe something which is counterintuitive, that if you excite a photocatalyst, it becomes both a stronger oxidant and a stronger reductant than it is. And that allows you, depending on the substrate, if your substrate is a good electron acceptor, so if it gets easily reduced, that allows you to do reduction chemistry from your photocatalyst. But if your substrate is a good donor and would like to give an electron to your photocatalyst, then the ruthenium-3 center here becomes a good oxidant. So you have both opportunities, and that is of course very useful. And so we will talk about this metal to ligand charge transfer today, and we will also talk a little bit about the opposite thing, that there might be also a ligand to metal charge transfer, where actually the ligand gives an electron to the metal center, and you will see that this can result in very different chemistry. So again, photo-induced electron transfer, this is what I have just alluded to. So typically you go to the excited state with your photoredox catalyst, and now depending on the substrates can get oxidized or can get reduced. And I show you the example here that the substrate actually gets oxidized, so it transfers now from the substrate an electron into the HOMO. And now also one thing which is important to realize, and then which can also help you very often in your reactions. You see, now you have created species which have charges. And especially you have here created on your photocatalyst, you have created a radical anion. And of course, charged species usually are not so stable. They try to get rid of the charges. So in the easiest way this could do is the photocatalyst, the reduced photocatalyst, could give the electron back to the substrate and say, suppose it say, leave me alone with the charges, right? We don't want the charges. And so in many, and you see, the electron transfer might be very, very fast. But the lifetime of the charge-separated species is still at best in the microsecond, but it also might only be nanosecond. One thing to help these type of reactions is that you do something which is called a proton-coupled electron transfer. And in the easiest way, in the most easiest way, your solvent will contain some water so that you have some protons. And what is the proton doing? The proton now can protonate your anionic species and take care of one of the charges. And especially if you have if you have an acid in there, maybe not even just water, acid, then your residing anion is highly localized, stabilized, and so that is a much better scenario than maybe having just a radical anion which comes from the photocatalyst, which might not be very stabilized. So that is a strategy you see very often if you want to do an electron transfer, that you do it in the presence of a proton source, and that term which is used for this is proton-coupled electron transfer, and that makes, and I show you examples for this, this makes these electron transfer chemistry very often easier. So here are the typical two cycles which we can get. As we already said, we have the excited state of the photocatalyst is both a better oxidant as well as a better reductant. And there's something we call the oxidative quenching cycle. And so in the oxidative quenching cycle, your photocatalyst will reduce a substrate. This way it becomes oxidized. This way, therefore, we call it oxidized the oxidative quenching cycle. And then your oxidized photocatalyst at some point, in order to go back to the ground state, needs to pick up an electron from a donor. That donor can be an sacrificial donor which you add in your reaction, or it can come also through the substrates. So also your radical anion here could be the donor, of course. If that would be the case, we would come back to the same thing. But if the radical anion is doing a reaction in between and then the adduct is transferring the electron back, we might have a productive process. And then there's something simply the opposite. There's a reductive quenching cycle in which the photocatalyst gets reduced and it takes an electron from a donor, the donor gets oxidized, and then the reduced photocatalyst at some point has to be able to give back that electron which it has picked up to another substrate, and this way go back to the photocatalyst. So this is the one type of principle which is very, very good and we can always use. And now the question is, now we have all these photocatalysts, which parameters are really interested for us? What should we know about? If you choose, and nowadays you can choose more and more and more photocatalysts, what are the parameters which probably are interesting for us? Absorption maxima. That's a good answer, right? Because you want, if your photocatalyst cannot absorb the light in which you irradiate, then of course your photocatalyst is not active. The one thing, and I will also show you spectra for this, the one thing which is sometimes very peculiar is you don't always necessarily have to take a lamp which will hit your absorption maximum. That is probably the most effective one, but typically if your absorption maximum, you have an absorption maximum and then my tail in the region, you can also irradiate besides this, as long as it still is absorbing light. So, and sometimes this might even have an advantage if you can go to a lower energy wavelength, so that you might not destroy your substrate. And I show you examples for this. But indeed, if you irradiate at the maximum of a catalyst, that's of course the most efficient one. Okay, so you give lots of answers here. Stability and reusability, absolutely. As always, one thing. I will argue maybe something secondary. If you think about scaling up to ton scale or so, then you think about reusability. And if we are completely honest, I don't know if you have run photoreactions so far. We do running photoreactions. Very often we are not trying to recycle them. I think it's really, it would be a good idea to recycle them. In our group, we use copper and iron a lot. Nobody cares so much about this. Redox potential, very important, right? How strong is the power of my excited state of the photocatalyst to either reduce or oxidize a substrate? And you need to know the redox potential, and you need to know the redox potential of your substrate, right? Because your photocatalyst has, for example, the power to oxidize with a certain power your substrate, but if that power is not sufficient for the substrate to accept the electron, then of course it cannot work, right? So absolutely redox potential, but both photocatalyst as well as on your as well as for the substrate, this has to match. Electron transfer pathways, how is the electron transfer taking place? That is indeed very important, and maybe even more with electron transfer pathway, you might want to express, can that electron transfer take place? Is it possible? And is it especially possible in an intermolecular reaction where you have a photocatalyst which is excited, thinks it's good, and then the substrate says, maybe I will find you, maybe I will find you not. And in this way, especially in intermolecular reaction, the excited state lifetime becomes very important, because if that is only very, very short, the substrate might never find the photocatalyst fast enough in order to undergo the electron transfer. So excited state lifetime is also a very important parameter. And I will show you activation modes. Maybe today, I'm not sure. You guys have to sit in here for a long session, but I have so many slides here, and you see I'm not doing this so very fast, but I think we're getting to this. I'll show you activation principles where the excited state lifetimes might not play a role at all. And this is the reason we might be able to use earth-abundant compounds. So that is the thing, and I already answered this. Why is the long excited state lifetime beneficial? It is beneficial because it gives you the chance to do an intermolecular reaction. Okay, so, and then we're looking, I can show you the same cycle which we have just had a little bit without data, but then very important, so here shown for the ruthenium BP, you bring it into the excited state, and now you have a negative number, and this negative number tells you how strong of a reductant it is. And the bigger the negative number, the stronger is the reduction potential. And so you're having a reduction potential, and this tells you, for example, if you want to reduce a carbon halogen substrate, if it can do this or not. And this is a number which doesn't tell you anything, but if you would now know the corresponding number of your substrate, how easy is it to oxidize, how willing is it to accept an electron, then you could see if it is matching or not. And then if you're at the ruthenium-3 state, you need to go back sometimes to the ruthenium-2, and so there's another number attached. Now it's the number, the ruthenium-2 wants to become, ruthenium-3 wants to become ruthenium-2, so the ruthenium gets reduced, in turn it wants to oxidize the substrate, and so now here's another number, this is positive now, and that tells you how strong of an oxidant your photocatalyst is. And you have this for the oxidative quenching cycle, and you have this in the same way you have it for the reductive quenching cycle as well. Here the reductive quenching cycle, you cannot see it for some reason, I don't know what happened to that slide. Triethylamine, for example, is a very good electron donor, and so here the excited ruthenium-2, if it takes up an electron from the triethylamine, it actually becomes ruthenium-1, which then is in the ground state a very, very strong reductant and can do this. And you see, it can typically then, depending which cycle you have, here you have a much weaker reduction power, so you need activated bromocarbonyls. If you can go through the reductive quenching cycle, you can actually do activated halides. So how can I switch between this? Well, if you want to be able to go through, if you need to go through the reductive quenching cycle because your substrate cannot accept the electron through the oxidative cycle, then you just have to add an sacrificial electron donor, right? If you do this, if you run the reaction with triethylamine, then it is possible to go through the ruthenium-2 because you offer a reductant. And that is something we see very often in this type of chemistry. And then for each and every of these photocatalysts, there are numbers available. You see here is now for an iridium catalyst, don't worry, but you see the numbers are changing. And I should have also pointed out that this was already on the previous slide. Besides the redox potentials, you have the absorption maximum, And then you have the excited state lifetime. How long is the excited state living? And again, that is quite different. The ruthenium is 1,100 nanoseconds, so that is already very good. The iridium complexes, this is why we like to use them so much, have even longer excited state lifetimes, right? So these are the three really most important parameters: absorption, excited state lifetime, and redox potential to do this. And with this, we can do this. Now the question is, how do we know all these? Do we need to measure it every time? Do we need to memorize it every time? And the good thing is, it's all in the literature. And there are reviews, a lot of reviews where you can look at the tables. There is a poster from Merck you can download from the internet. And you see what they did here. That's pretty cool. They have listed all types of photocatalysts. And then they say, these photocatalysts can either do oxidations or reductions. But then you see also what they have done. They have listed all types of substrates here, substrate classes. So you can look, how strong is my photocatalyst, how good of an oxidant it is, and how easy then is my substrate oxidized. And you can see that you can then match this. So if you would take this catalyst which has a weaker oxidation potential, but you need a substrate here which is hard to reduce, then it wouldn't work, right? And so very easy, in an almost very predictable manner, you can use these type of tables, and you can see, now I want to do this type of reaction. Do I have a chance? Do my potentials match from the photocatalyst? And very often you might use new substrates. You will not use so often new catalysts, but you might use new substrates. Then you might have to be able to measure your redox potential, but that is a redox potential you measure in the ground state, right? Because you bring your photocatalyst in the excited state, but then when it transfers an electron to the substrate potential, which is interesting, is the one in the ground state. And for this, you need to, how do you measure the ground state oxidation or reduction potential? Have you done this before? What is the methodology you use? You use a cyclovoltogram, right? A CV spectrum, exactly. So essentially you have your substrate, you put on an electrode, you put on a current, and then you have a line, and then the moment it gets oxidized or so, then you see a signal change, and relatively easy to do, and I'm pretty sure you guys all have. You have a CV spectrometer here, right? Sangeeta and I were discussing intensively that we need oxidation potentials of phenylacetic acids, right? So yes, so that's the way to do it. And I give you here another publication which very nicely lists all the types of oxidation and reduction potentials. And earlier we talked about bond dissociation energies of substrates when we talked about atom transfer, hydrogen atom transfer. Here I point you to another publication which lists you the bond dissociation energies, and so it gives you at least a good idea. And also when you write later on your thesis, it also, sometimes reactions still don't work, but then always try, even if a reaction doesn't work, try to make a story out of this, right? Say, don't just say it didn't work, I go to the next reaction, right? Say, always make clear that you had a pretty good idea why that should have worked, right? You could have said, oh, so my oxidation potential of the catalyst matched the reduction potential of my substrate, right? And so I checked this up, and based on the literature precedent, that should have worked. And now it didn't work, and then maybe you come up even with an explanation. But very often you can spin a good story even from experiments which has not worked, and that is something you should always try to do and reflect on this. So again, lots of data and which you can get out of this, and then there are very good photoreduction catalysts, very good catalysts which can reduce substrates, and then there are also very good substrates which can do actually oxidations, and we will look a little bit about around this. Okay. One thing which also, again, it's a little bit more physical, and there's no need to remember this or recognize this, but the one thing, nevertheless, to keep in mind is that the photoreaction can only work when the delta G is smaller than 0, right? That's the usual thing. And so you need to see that your oxidation potential of the donor, so the donor gives a substrate, gives an electron to your acceptor, that the oxidation potential, the difference needs to be, and I would say in the first thing, needs to be smaller than 0. That would be true for the ground state. But since you give excitation energy into your system, so you start the chemistry from the excited state, this energy makes the process more negative, right? So that makes it more favorable, and you can, that is why photochemistry has become so useful, because you can go beyond the ground state potentials. They might not give you a delta G smaller than 0, but then if you argue from the excited state of your donor, for example, of your catalyst, then you might be okay, right? And so the excitation energy, again, it's all known in the literature, but you could also measure it from the emissions spectra. And then there's something in addition, there's something like a Coulombic term, and it's already written there, solvent-dependent, often neglected in polar solvents. But that reflects the way that you're making charged species. And if you're in an unpolar solvent, charged species are not very happy, right? Because they are more or less naked, and then the process again becomes harder. So that is a positive term to take into consideration. And so therefore I could ask you, what are the most popular solvents we very often use in photochemistry? And now you can probably take it from what you did yourself. What is it typically which you use? Acetonitrile. That's indeed, right? That's a solvent we all like a lot, really a lot, right? It's actually not such an inexpensive solvent. We use it a lot because we do small scale. But if you run to your boss later on in a company and say, we are having this great batch process and we need 2,000 liters of acetonitrile every time, he will say, can we use something else maybe, right? That might be good. Okay, so you guys like acetonitrile? Very good. You like also acetonitrile water. This is what we're doing a lot, that acetonitrile, and then we use a few percentages of water or so. And then in some cases even lots of water even. So Sanchita has a reaction where she is using 10 equivalents of water and only 1 equivalent of the acetonitrile, just to keep, as I say, acetonitrile is not the most inexpensive solvent to bring this. So this is the one thing which is also nice, is that acetonitrile and water are miscible to a certain extent, right? DMSO is a similar solvent. It dissolves essentially everything, and therefore it's good. Water is in principle very good, but it doesn't dissolve a lot of organic compounds. So that is also, people do very successfully also photochemistry in water, but this might be the difference. So what you see here is, automatically probably, without maybe aware of this Rehn-Weller equation, you guys are all using polar solvents. And that is exactly the point, because then you're not working against the Coulombic term here, because these polar solvents will stabilize your charged species. And so you're okay. If you would have been doing the reaction in cyclohexane, then there would be no stabilization of the charged species, and therefore your Coulombic term would hinder your reaction, right? And you can measure this. You can measure these Coulombic terms, and you see here exactly what you would expect. The Coulombic term becomes smaller and smaller the higher the higher the dipole moment of your substrate is, right? And so water would be ideal from the polarity, with the downside that it might not dissolve your organic compounds. And that is why acetonitrile is a pretty nice choice. And you hardly ever see that a photoreaction is being done in benzene as a solvent. As a substrate, that might be a different idea. Okay, so then electron transfer, as we said, occurs from the excited state. the delta G should be smaller than 0, then the reaction should be thermodynamically run. But interestingly enough, it can also be even a little bit positive. So as you all know, it's typically equilibria, and you can tolerate that it is even slightly positive, but then very important, you need to, because then you start generating your charged, your species only in small concentration, you need to have an irreversible event which then quenches the step. So typically when you have a donor and this gives an electron to your photocatalyst, then you can, if this is thermodynamically uphill, you need to make sure that your photocatalyst, the reduced form, is deactivated by having an acceptor present. And then you can have, as I say, roughly rule of thumb can be 500 milliampere uphill if you can take care of your charged photocatalyst in a subsequent reaction. Right. We will talk about energy transfer. There, the hole between singlet and triplet must match again with the substrates, but we talk about this a little bit tomorrow. One thing I can also not stress enough, that goes to the fact of reproducibility, is that it's not only reactor dependent, but also it's LED dependent, and the intensity of the LEDs are changing relatively fast. So you use an LED, let's say for 1 month every day, and you measure the intensity, and the intensity might be a lot lower than it was at the beginning of this. And so you need to measure periodically. That's what we do in our lab. We measure periodically the light intensity, and that is not so difficult to do, and this is the measurement is actinometry, and we have actually the apparatus to do this. But the idea is that you have a compound which you can transfer, and you see this is the nice thing. This is essentially redox neutral. The nitro group here gets reduced to N oxide, and the aldehyde gets reduced to the carboxylate. This is a reaction where the quantum yield is exactly known, and then you can measure, and simply by the change in absorption, how your starting material is converted with time, and this is directly proportional to the light intensity. And so you can relatively easy check your LEDs, and you should do this probably really once in a while, once a month, depends how often you use it. But this can make a huge difference in the efficiency of your reactions. Right? Another important aspect is quantum yield. So one photon, can it run a reaction, or which percentage of the photon can do this? And so typically a quantum yield in photoredox catalysis we see between 0 and 100, and 100 is already pretty big. We see very often much lower quantum yields, and that again is an expression that the energy efficiency might not be so high. But sometimes you see very, very large quantum yields, 100,000. So that means one photon will trigger 100,000 reactions. That is typically an indication that you run through a radical chain mechanism rather than through a photoredox type process. Okay, ways again also to measure the quantum yield. I don't know if you have any apparatus of this. We have one which we have a photocatalysis center which we have built ourselves, which is essentially very easy to use, where we have our probe here, our sample. We shine light through the sample, and then we can detect how many photons are arriving, and then we can correlate this with the yield, and this way get out the quantum yield out of this. Again, typically, also when you publish paper, the reviewers more and more ask for quantum yields in these photoreactions. So you need to see, and I'm pretty sure you guys have that capacity here as well. I would like to talk just very quickly, show you a few pictures, how to set up photocatalysis reactions. So which photocatalyst should I use? We talked about this. Sufficient redox power must be given. Your excited state photocatalyst must be able to interact with the substrate. That is something you can test with these so-called Sternformer quenching experiments, where you measure the decreasing fluorescence when you add substrate to your photocatalyst. And if the fluorescence is quenched, this is an indication that your catalyst is interacting with the substrate. Again, very important to check these things. We talked about the solvents. Here again, I give you a table simply of the polarity and also the cutoff. Again, very important. If your solvent would absorb where your substrate, your photocatalyst absorbs, then that solvent would be useless, but by and large, most of the solvents, or virtually all of the solvents you have, are transparent in the visible light range where we typically want to irradiate. Right? Question is, should we avoid oxygen? And the answer is, in many reactions, yes, because oxygen might itself absorb the light and form singlet oxygen, right? And so that can be a nuisance, but there are, of course, exceptions, and exceptions are when you actually use the oxygen maybe as a reagent. And I haven't had the chance yesterday to show you that these cyclopropanoyl furans we can do a photooxidation in the presence of oxygen and then form such peroxides where we actually have incorporated the oxygen. And so that is a case where we actually need the oxygen, and also as an electron acceptor in this case. And so that might be, this might be indeed sometimes very useful. Sometimes you need the oxygen to reoxidize your photocatalyst, to close a cycle. So that might also be very useful, right? Light sources, as we have discussed, the best thing are indeed there are many available, but nowadays we all do LEDs, and that range is expanding further and further. We just saw recently that you can buy now 300 nanometers or even 280 nanometers LEDs. They are expensive. Then suddenly one LED is a few thousand euros, and that is good. That is more expensive. Sometimes you see these so-called CFRL lamps, compact fluorescent light bulbs. That is always a little bit tricky, at least if you want then to make an assumption how your reaction works. Sometimes it's good then to use it because it makes the reaction work, but you need these typical energy saving lamps, very inexpensive, but the problem is very broad emission of light, including UV parts. So then it makes it a little bit harder to understand what is actually going on. Typically, you can, with the LEDs, you can irradiate from the outside. If you're in the visible light range, you don't need special glassware. You can use the normal glassware. Internal irradiation might also be quite nice. And I just show you, and you can compare. You have probably similar apparatus. This is what we use a lot. We have these type of plates where we can put reaction tubes in there. There's a cooling from the inside, and then we shine lights from LEDs. We have LED plates inside here. You see it now, it's irradiated, which you can do it. And that is pretty good already because we have relatively low light going outside, and which could harm yourself. Right here it's shown again, and I'm sure you have things like this as well. We actually built these in our machine shop. So here the water cooling, and then you see this is the plate with the LEDs, and you can just put them inside and run the reactions, right? This is something I like a lot as well. This is something we build, and you probably can also very easily build this. This allows you to do irradiation from the inside of your vessel. And the way this works is we have an LED up here. Right? The LED is up here. It's not down here. And then there is a quartz rod going in here, going in this. And so we essentially put light on the quartz rod, and that gets transmitted all the way down to our reaction flask. And you can see this here. We have in detail described this type of apparatus and how to buy it, it's really inexpensive to do it. We have described this in this publication, and again, you have the handout, so if you're interested in this, you can look at that. The big advantage this might have, we can only use it on small scale, but the big advantage this might have is that we can run a reaction now where we can put on the outside, we can put a heating bath or cooling bath, right? So we have a very good way to do, let's say, a reaction at minus 20 degrees or at plus whatever. And this is why we actually like this type of technique. It's a very low cost technique, but it has proven for us very efficient. You see we have a Schlenk tube here, so we can introduce gases very easily as well. So that has been good for us. And then some of our students have funded a company, so they sell more professional type of things, and they don't give us discounts any longer. It's something I find very disturbing, but this is a little bit more professional, and you all know this. We can build them, but now the sky is the limit, right? You can buy also these reactors for a lot of money, right? Okay, and then here, this is just, I have the advertisement from the company, from our students, photoreactor.de. I have it in there. Last question for the general introduction. If you have a 1 millimole solution, that's not a lot. That is typically lower than you might do a reaction. And then if you shine light your LED from the outside, let's say a 450 nanometer LED, how much will it penetrate into the flask? Right? And so, okay, one brave person said 1 nanometer. Okay, so you like the nanometers. So that is pretty scary, right? You have a flask, which is usually in a diameter of several centimeters, and it would go 1 nanometer. That would be very, very little. Okay, so I can see here you guys are not completely sure and convinced. Now the top contester here is the millimeter. So we all have the feeling it's probably very little, right? And so indeed, if you look at this was here measured in this publication. They had a 0.5 millimolar ruthenium catalyst. DMB is similar like to the BP, and then you can see now in different types of concentration of that photocatalyst, you can see it's in the millimeter range, but even the most diluted catalyst, you see the transmission is at 1 millimeter is already down to 20%. So that's not a lot, right? If you think about this, if you have a huge flash and you put your LEDs around this all the time, it goes only in a tiny, tiny way. And so increasing the surface is a very important technology to speed up reactions. And that is why flow chemistry has become very important, because in the simplest way, flow chemistry sounds great and expensive. We will talk a little bit about this. But in the easiest way, you just take a tube and coil it around your photo lamp, right? And then you pump your reactions through. And essentially that increases the surface and gives you much better intake of light, and in order to do this. Okay, so this was the first part, just some principles on this, on the photocatalysis idea. We started 2:30, right? So we took exactly an hour. That's pretty good. And so we can continue with some applications. So we now talk about some applications, and I would like to talk about, wait a minute, I don't have, okay, I thought I had an introductory question. So I would like to start with single electron reductions. Because that's probably the most common type of photochemistry which you can do. And let's look at a few reactions, and some of them I will will not discuss in detail, but I would like, because we have that official tutorial, I would like to discuss a little bit more mechanism with you a little later. But let's simply look at a few reactions. And again, it always amazes me what was known and what was done already in earlier times. Here, so Kellogg, 1978, right? So essentially 30 years before we had this big resurrection of photochemistry. And so look what he did. He used a sulfonium salt. That is similar, look here, it's almost the same substrate like a bromine. The sulfonium salt, without even knowing the reduction potential, you probably have the idea that this should be relatively easy to get reduced and probably relatively hard to get oxidized, right? Because if I oxidize it, I take away an electron, this is already positively charged, then I would make it even more positive. And we all know organic compounds hate too many charges. But that should get relatively easy, it should be easy to reduce. And so that's exactly what they did. And you see here already, they did everything. Ruthenium bipi, visible light, acetonitrile, I mean, it was all out in the literature. And they did a simple reduction here. And we need to talk about how these mechanisms overall go. But you see, if you make the radical here, you make this radical, then this radical, one way to get the reduction going is that it can do a hydrogen abstraction from a hydrogen donor, which you will provide. And this publication is use these type of Hunch esters. And of course, who has invented this? Who has invented this type of hydrogen donors? And hydrogen donors, nature invented this, right? So NADH and so on. So nature is using these type of donors a lot, simply for the fact that you might end up in an aromatic system once you lose a hydride here or once you lose a hydrogen atom. So they went through the radical and then realized that hydrogen abstraction from these dihydropyridines is very efficient. And then the question is, if we do, and then I should use the pen. I should use the pen, but so pen, but the pen is gone. Does anyone see the pen? We lost the pen. It's in there. Thank you so much. Is it on? Yeah. So let's look at the pen. So the one thing you always need to look at is, so we start here with ruthenium 2 plus, right? And we bring the ruthenium to the state of 3 plus in order to deliver an electron to the substrate and then ultimately make this radical, which is being shown here. So the one thing to always to remember and consider, and I would like to discuss with you a little bit more in the talks here, at some point we need to bring back the ruthenium from the +3 state to the +2 state. That's very important. And so if this radical is doing a hydrogen abstraction, then we only have this radical, right? And so at that point we have the product, but we have not closed the catalytic cycle. And so now the question is, how is the ruthenium 3 plus going back to the ruthenium 2 plus? So it would like to get an electron from somewhere, and this is exactly where it can get it from. So if we have ruthenium 3 plus going back to ruthenium 2 plus, then in change we are going to oxidize. You can see I have always a little bit problem with writing on these things, but then we are going to oxidize the substrate. And this has a very high driving force to get oxidized, because I can draw a resonance structure. I will do in the next one. I will do this again on an open page. But you can see that this is a resonance structure from a ring, right? And so that's why I say this is what nature is actually doing. Nature is transferring hydrides very efficiently to substrates. But what it can also do, what this Hunch ester can do, is it can transfer a hydrogen atom, and then in the next step gets oxidized by the photocatalyst, and the driving force is very high because it makes an aromatic system, and this will bring back the ruthenium 3 to the ruthenium 2. And so you're probably also very much aware that you always, when you design photochemical reactions, you need to think very carefully how you can close the catalytic cycle, and very often the first step is very often very clear to us, and there's the moment where we correlate oxidation and reduction potentials with each other. But in many cases the second step might not work, because then suddenly the potentials might be wrong, or you might not, I will show you an example, or you might not actually have something which can, like in this case, do the reduction because you don't have a substrate which you can oxidize. So that's equally important. And so you see here more examples. Again, an example which I think is also from 1990, and you see again the reduction of the alpha bromocarbonyl compound. Again, ruthenium bipi acetonitrile, same idea. Here you see they have a different type of hydrogen donor to use here, but it's in a way it's also like a dihydropyridine, right? And then in a very nice publication 20 years later, the group of Corey Stevenson showed that you can do the reduction of these benzyl halides, and they used this because this was intermediates in natural product synthesis for them. But you can also see here that the conditions, ruthenium bipi, Hunch ester, this is all very similar, right? So the principle was definitely known at that type of place. So that's a reductive defunctionalization. That might not be the most useful ones. One thing which also has become very, very popular are these aryl diazonium salts. Why is that? Because nitrogen is such a fantastic leaving group, right? And so again, what you can do is, if you do an electron transfer, again, so the ruthenium, you see again, is positively charged. That's a good indication that it wants to get reduced. Electron transfer to the aryl diazonium salt makes nitrogen as a leaving group, and it makes such a phenyl radical. And this phenyl radical then is able to attack a second aromatic moiety, either with the benzene ring here or with the furane ring here, in order to make such coupling reactions. And again, this is something I would, let me see, do I have it in the tutorial, or can we discuss it here right away? Nope. So let's think about the catalytic cycle. So we have the aryl diazonium salt here, and our ruthenium catalyst, ruthenium 2, in the excited state becomes ruthenium 3, and it gives this electron to our substrate, so we're forming an aryl radical and nitrogen. And the arrow radical, let's take the example below here, might add now to the furane ring. Forming a new radical here. Let me see if I have this as a question. Yeah, I have it as a question. So we are here. So how do we bring now the ruthenium-3 back to the ruthenium-2? How do we close the cycle? I can show this to you here again. So I think it's pretty clear how we get to this point. How does the reaction proceed? Somehow we need to bring back ruthenium-3 to ruthenium-2. How do we do this? Okay? No idea or too simple? Probably too simple, right? What's going on, guys? Are you on strike or is it not working? Let me check my Slido. Okay. So somebody says reduction of ruthenium-3 to ruthenium-2. I mean, obviously, of course, this would close it, but how? How do we do this? How do we reduce, this will close it, right? If we reduce the ruthenium-3 to the ruthenium-2, that is the reduction step. But in order to do this, we need to oxidize something. So what are we oxidizing? You must help me out here. DMSO. Did they use DMSO? DMSO is a pretty good oxidant. I would give this to you. Oh. Jesus Christ, yeah, eosine. They didn't use, okay. They used DMSO in the second reaction. In the first reaction, it's, by the way, the very same thing as acetonitrile. BF4 minus converts to BF3. This would not be a reduction, right? That's simply elimination of fluoride. Unless you want to suggest to me that you oxidize the fluoride to the fluorine radical. That would be probably very difficult, right? No, it's much easier, but you need to keep in mind, and that's, so maybe it's good that we talk about this. I mean, the reaction is not finished here. And so what needs to happen now here in the next step is you oxidize your arene, right? This intermediate. And so if the ruthenium-3 plus goes now to ruthenium-2 plus, right, that ruthenium gets reduced, then it could oxidize the radical here to the cation. that is very often a very normal step, that the radicals can both either get reduced to an anion or can get oxidized to the cation. And then I think it's almost easy, right, with any type of base, water or whatever they have here. This is not like an electrophilic substitution on an arene, right? And now this way you're forming the furane, and you have regenerated the catalyst. So very importantly, most of the times you might have indeed a sacrificial oxidant or reductant in here, but very often it's the substrate itself. So that was again kind of an interesting and very interesting reaction, and very useful to show that this goes in a photochemical regime. Have you seen that at any point before this in your life, that, or in your lectures, that you take an aryl diazonium salt and you bring it together with a one electron reductant and do chemistry? You don't even need light for this. Under thermal conditions, you remember a reaction, I would say first year organic. Yeah, thermally, but how? What's the reaction? It's a name reaction. Homolytic diazotation. Okay, I'm not sure what this is. So the first name we're getting here is Sandmeyer. That's a pretty good answer, right? Let me make up a new slide. Right, of course, the Sandmeyer reaction, that's somewhere where we know this from. Oh, interesting. Now it's giving me a different color. So if we have an aryl diazonium salt and overall want to do nucleophilic substitutions, if this goes by the stepwise pathway in order to get the nucleophilic substitution, if this would go stepwise by extruding the nitrogen, you would make this cation, right? The phenylcation, that is a very, very unstable cation. It's not resonance stabilized by the aromatic ring. And so if you rely on this reaction, that works. For example, if you have something like HCl or so, you can do this type of reaction, or sodium hydroxide or so, but it requires 150 degrees or so. And so for the longest time, people have used copper salts, copper 1 salts, copper chloride, with the idea that now instead of forming the forming the cation, it forms the radical and copper 2 plus. Right, so copper 1 goes to copper 2, gives 1 electron to the aryl diazonium salt. This eliminates nitrogen. And now if this recombines with chloride, then 1 electron is being given back to the copper, and you reform your copper catalyst, right? So that's the Sandmeyer reaction, and that is of course one reaction we have applied quite a bit. Right? Why is the phenyl radical this one? the more stable intermediate than the phenylcation? How would you argue this? Didn't put this up at Slido, but what would be your argument that you say it's a good idea not to go through the phenylcation, it's an energetically better way to go through the phenyl radical? Why is this? There are only very few rules in chemistry, but you need to keep with them and always keep them in mind. So the rule you need to apply here is the octet rule. So why does it help us? Why does the octet rule help us to say the phenyl radical is more stable than a phenylcation? Why is the octet rule helping us? How many electrons is the phenylcation away from happiness? Happiness is 8 electrons. How many electrons? 2. And the radical? Only 1. So the radical is already closer to happiness than the cation, right? The simple reason. That's why it's more stable. So octet rule is really a concept you always need to think about if you can explain something with this. But this is the famous reaction David McMillan had developed in 2008, and I think we were all blown away when this publication came out. He was able to show that you can use aldehydes and do an asymmetric, let me see where is the product, and do an asymmetric functionalization of this aldehyde, and he used the malonate radical. And he did this in a very ingenious way. You have a number of cycles. He was not functionalizing the aldehyde, he was functionalizing the enamine. He has an amine catalyst, so the amine and secondary amine and aldehyde is making an enamine. That is pretty much okay, and I think you all know this. And then he had the ruthenium bipi, and the ruthenium bipi is again reducing the bromomalonate. It injects an electron and it takes out the bromide goes out, and then you have the malonate radical. And now look how nicely this is matched, because now you have the enamine, and the enamine is what? Electron rich or electron poor? Enamine is electron rich, right? This is like an enolate or so, right? Enamines are nucleophilic on this carbon. So this is electron rich, and the malonate radical is electron poor, right? Because it has these 2 acceptor ones. So this is an electrophilic radical, and this is a nucleophilic substrate. And so they are perfectly matched. And then if this malonate radical adds to the enamine here, you form a new radical. Let me see where I have it. You see, then you form this radical here. And if this radical, now you have oxidized your catalyst, now you need to reduce your catalyst. But amines are very easily to be oxidized in turn. And so in order to regenerate the catalyst, in order to go back from ruthenium, okay, I need to be careful, because I'm sorry, we could have done it this way, but he didn't do it this way. So he had also a sacrificial electron donor in there. He has also, in addition, he has lutidine in there. So he goes through the reductive quenching cycle. So from the ruthenium 2, he's first making the ruthenium 1, and then the ruthenium 1 is generating the radical. And so that's, once he has this amino radical, now it's just he needs to bring back ruthenium 1 to, he needs to bring back, now I'm getting confused here. He needs to bring back the ruthenium 2 back to the ruthenium 1, and that is what is using, where he is using this amino function here. This can get oxidized. This brings then again back the ruthenium 2 to the ruthenium 1 as a strong quench, as a strong reductant. And if you have a radical cation here and a radical here, this is the same thing like an iminium cation, right? You can redraw this So when you oxidize, this to the radical cation, the nitrogen, then you see now you have two radical centers next to each other, and this is essentially a measurement. Now you can draw the bond between nitrogen and carbon, and this is the same thing like this iminium cation. And then if this iminium cation gets hydrolyzed, you're getting the aldehyde back, and this way you have alkylated the product. And since he's doing this with a chiral organocatalyst, the reaction was highly enantioselective in addition, right? So it's perfectly matched between stereo control through the organocatalyst, but also the match of generating an electrophilic radical and a nucleophilic alkene in order to make the coupling possible and then to regenerate the catalyst, in this case in the reductive quenching cycle. So let me point this out. Again, you start with ruthenium-2, you bring it to the excited state, but rather than at this point transferring an electron to the bromomalonate, what they're doing is with the amine, they're reducing the ruthenium-2 to the ruthenium-1, and this will then reduce the bromomalonate. Okay, so great example. Here's another example how you can make radicals, and that is something I think is also a tremendous and fantastic technology, and that was developed by Okada already in the 90s. And he did also a very interesting way, because what he did is he's using the carboxylic acids, and then the carboxylic acid, he's making these phthalic esters out of this. That is relatively easy to do. So if you have a carboxylic acid, you can activate this as an acid chloride, and then these hydroxyphthaleamides, commercially available, can do this coupling. And now if you inject, you see here again is ruthenium. If you inject an electron into this molecule, so you go from ruthenium-2 to ruthenium-3, so then you transfer an electron here, and this intermediate is able to fragment. You see it can break the NO double bond, NO single bond in half, and takes the electron with it here. You see then it forms the new, if you look at this from the point of the phthaleamide, it forms such an enolate type structure, and importantly, it forms such the carboxyl radical, and the carboxyl radical extrudes carbon dioxide and forms a radical. And this radical he can do for chemistry. This is something I would like to discuss with you later in the tutorial. You see, again, you form an alkyl radical. The alkyl radical is added to, as a nucleophilic radical, is added to the alpha-beta unsaturated carbonyl compound. And then in the end, and we need to talk about this, but this is something I want to do in the tutorial. it somehow needs to take up a hydrogen here, but then at the same time, we still have the question how we bring back the ruthenium-3 to the ruthenium-2. So we need to look at this, but I want to look at this because I will show you a related process which works different in the catalytic cycle, but makes the same product. And so this is why I would like to bring this together. So this has become a very important technology, very widely applied. And because these phthalic esters from carboxylic acids can be so easily synthesized. And look also what Okada had already realized, without really putting this clearly in the paper, but he's having a mixture of THF and water in his procedure. And the water is protonating the negative charge here. And so again, this is an example, again, of proton-coupled electron transfer. And with the water, it goes much better than without. And you can debate if the proton first, if the proton then coordinates to the anion, or if the proton, you see, the proton can already coordinate here to the carbonyl group, and then the electron transfer becomes easier. And I think this is actually the better mechanism to look at this. And so many examples. Our group also has contributed to an example as well, where we are generating the radical on this position, and then once the radical is formed, it can undergo a cyclization into the arene ring and then a rearrangement throughout the carbonyl group and make chemistry. I don't want to go into this. You will see enough advertisement from our chemistry a little bit later. So again, carboxylic acid activation. Also at that point, maybe already keep in mind, I think we have seen this also already a little bit. So you can do the activation. You can do the activation by photocatalysis of a, what's doing now? Okay. All I want is a new slide. Give me a new slide here. Now it shows me this toolbar here, which homepage. Sorry? Homepage. Sorry. Yes. Oh, okay, you're very good. Okay. Excellent. Right. I want to point out to you, and again, this is quite useful. If you have a carboxylic acid, and this applies also to other substrates, I have just shown you this technology where you make an activated ester, and now in order to go to the carboxyl radical, you take a photocatalyst which will add an electron, right? So for example, we have the ruthenium-2 catalyst, which will become ruthenium-3, and then this way you're getting the radical, and in this case, after the fragmentation and protonation, you get this one. As we said, it's a electron-proton coupled transfer. But also note here that with the base, you might form the carboxylate, and you see now you can arrive at the very same radical But now the difference is that you're not doing a reduction, you're doing an oxidation. So you need essentially so you need to take away an electron, and so you need a catalyst which can do oxidations, right? And one of the catalysts which people have used a lot now is iron 3, which might become iron 2, or copper 2, which might become copper 1, right? So it's an interesting thought that you can make the same type of radicals either by reductive processes, where you have typically a pre-activated substrate, or by an oxidative process. I showed you earlier that you can take these malonate radicals. It's the same thing. You can make the malonate radical from the bromomalonate, and there you need to put in an electron to make this radical, and in this case plus bromide. And the alternative is to start from the malonate with the base, make the anion, which is of course for the malonate very easy, pKa of about 10, so you can easily deprotonate. And now if you do have a photocatalyst which can do an oxidation, so you take away the electron, you're again making the same radical. But you always need to think about how do I close the cycle, because for example if I go here from ruthenium 2 plus to ruthenium 3 plus, I need somehow, in order to close the cycle, I need to go from ruthenium to 3 plus to ruthenium 2 plus. And the question is, how do we do this? And here it could have been, for example, copper 2 plus to copper plus. So we are reducing our photocatalyst. But now we need to ask ourselves over here, how do we go from copper plus back to copper 2 plus, right, in the course of the reaction? And that's something I would like to discuss with you also on in the context of the tutorial. Okay, here are a couple more concepts which one can use. So again, a proton-coupled electron transfer. This is something we have seen already a number of times, but there's another interesting twist to this, again, very nice publication which came out a number of years ago, now more than 10 years already. Time is terrible. You see here in this case, you're exciting the carbonyl group, and we have seen this, that you can do if you inject an electron into the carbonyl group, you get a radical anion. And again, you do this in the presence of an acid, because then the anion gets quenched by the proton and you are just forming a radical. And what is very nice here, in this case not so much. Again, this is a nucleophilic radical. This is what we have seen in this Felicity scale, that these alkoxy, the radicals from alcohols are very nucleophilic. And you can see there's in a very good distance, there's again an alpha beta unsaturated carbonyl group here, functionality. And in the 1, 2, 3, 4, 5 exotrophic ring closure, you can then achieve this type of cyclization here. And again, the protonation of the carbonyl group makes the subsequent electron transfer easier. Okay, and so there are more examples of this type. Let's not really go into this too much. Here's another thing which I would like to point out, which is also for me, you will see in a moment a basic reaction, which was in a brilliant way executed 40 years later. I show you here an example from 1981, and then I show you on the next slide an example from 2023, and you will see this is spectacular what you can do with this, and also always spectacular what you can do with this if you read older literature carefully, see what was accomplished already, and see if you can build onto this. See here again, it's a reduction. It's a reduction reaction. So the ruthenium 2 plus is able to, in this case, is able to transfer an electron to make ruthenium plus. To make ruthenium 3 plus, it transfers an electron. I need to draw this, then it's easier for me. So here we have ruthenium 2 plus again to ruthenium 3 plus. And this electron goes into this acceptor. And that is the, again, very exciting thing. It makes such a radical anion. And this radical anion, of course, is not particularly stable, but if you do this, you see here in this case of methanol, you have a proton source, and you are able to protonate the anionic part, and then essentially make the radical. And then in this case, what these people did is they have again a Hunch ester available, and I have asked this to you, but we have already discussed this, how this goes. This can make a hydrogen abstraction to form the product here. So we have the first hydrogen from the proton. Now it's doing a hydrogen abstraction, and the resulting radical here, which I'm getting out of this, in the presence of the ruthenium 3, gets oxidized. And this is something which works so well because, again, the driving force really is that upon oxidation you're forming an aromatic system, right? And so therefore these Hunch esters are good hydrogen donors, but at the same time they are very good reductants because ultimately they want to transfer hydride to make the aromatic system. So that was known in the literature, and actually quite attractive, right? That you can make such radical anions and then by protonation to make the radicals. And in 2024 even, this concept was used again, and I think in a really brilliant and spectacular way. It's the same idea. So you have a photocatalyst. They're using a stronger photocatalyst than we just had with the ruthenium bipi, because they are not only able to reduce the fumarate here, or the malate. You will agree that this is pretty easy, right? Because it has these two electron withdrawing groups, and therefore an electron can very easily be introduced in the system. So they used a stronger reducing catalyst here, this organocatalyst, don't worry why this is, and are able also to reduce styrenes to the radical anion. Right? Same idea, it's just written here as the with a dotted line. Let me see, do I have a question? No, I don't have a question. And so again, here in this case, they're making from the styrene, they're making the radical anion. Let me get a slide here again for drawing, because there's something I would like to discussed with you also. So they have the styrene, and now are able, with this very strong reducing catalyst, they are able to make the radical anion. But you see, with our malonates, we had two ester groups. So that was symmetrical. But now with the styrene, it's unsymmetrical. So you're forming now, and you can draw it either way. You're injecting the electron, right? So I can draw it as a radical anion here. So I put the radical, the anion here. Or I could have also put in the negative charge here. So that's a resonance structure. And now if this is trapped by an electrophile, proton in the easiest way, where will it go? Will it go here? Or will it go here? It wants to go to the negative charge, right? No question about this. But which one is it taking? Which of the two carbons is the electrophile attacking? Which one? The terminal one. This one. Well, why is this? You see, this is also good for oral exams. Whenever you answer something, you can, in an oral exam, when you have an oral exam with me also, you can answer whatever you want. I will never say yes or no. I will also always say why. Right? So you had a 50% chance to be right. Congratulations, you are right. But why is it attacking the terminal end? Why is it not attacking here?
After taking the proton,
Yeah.
the radical will be stabilized by the.
Absolutely, right. This is the good idea. So if we continue writing this, if we attack here, we are making a benzoic radical. If it would have attacked here, we would have made a primary radical, right? So the protonation is dependent on the radical stability of the next step. Very good, exactly. And so now, if what they did is, so we see this here. So they have the radical anion. And then the radical anion gets trapped by the proton, and we are forming this new radical. And now they did something really, really nice. What they have is, they have as an additive, they have copper 2 salt in there. And I told you already, copper 2 is D9. It's itself a radical, but it's a persistent radical. And they have the copper 2 coordinated. They have the copper 2 coordinated to a chiral ligand. So this is essentially how it looks here. And now the resulting radical, which they are forming, so this is copper 2, and so it has the ligand here, don't worry about this. And now the radical they are getting is very rapidly getting trapped by the copper 2 species. And so it forms a copper 3 intermediate. And this copper 3 intermediate, if this undergoes now a reductive oops, go away. There's an insect here. Yeah. And so they do this in the presence of TMS cyanide. So one of their ligands which they have here is the cyanide. And then if this is doing a reductive elimination, you see here this is the same intermediate. Here they have the radical trapped, and then the cyanide is also coordinated to the copper. If this is doing a reductive elimination, then they introduce the cyanide onto the benzoic position where the radical center was. And because the copper catalyst is chiral, they have been able to do this in an asymmetric way, and so they are able to obtain cyanated products with very, very high, you see here some examples, very, very high enantioselectivity in doing this. And I think this is really nice and very spectacular. They have also been able to show other electrophiles. They have also been able to show deuterium, or also a very popular electrophile these days is carbon dioxide. So you're not limited to the proton, and can do these type of alkene functionalizations as I say, in a very stereoselective and spectacular way. Okay, so then we have one more example, and this is also something which I believe is also very instructive for thinking about cycloaddition. So 2+2 cycloadditions, I'm sure you're aware of, you can typically do by photochemical sensitization of two alkenes, or typically even better, the one, I'm still on this, yeah. Right, if you have two alkenes, for example, two of these, under light irradiation, the 2+2 cycloaddition is photochemically allowed, and then you can this way generate 2+2 adducts, simply because one of the alkenes gets into the excited state and then reacts with the other one. But originally, the group of Pandey, Ganesh Pandey, I don't know, is this a name which is known here in India? Right, he's I think he's one of the really heroes of photochemistry, who already in the 90s made spectacular contributions to this. And then later on, more or less the same reaction, but with other type of photocatalysts, the group of Yoon showed that as well, that instead of doing an energy sensitized 2+2 reaction, which is, I guess, the more normal one, the way this can also work is that you can do start the 2+2 cycloaddition by electron transfer. And you see what they're having here. They have these alpha-beta unsaturated carbonyl groups, and if this gets injected an electron from the photocatalyst, you are forming such radical anions, as it is shown here. And these radical anions, again, we have seen now many reactions where the radical is adding to an alkene. If you look at this radical anion here, would you think it's nucleophilic or electrophilic? What's your feeling? It's nucleophilic, right? Because it's already an anion. That is probably normally a pretty good indication for this, right? And so again, you have an electron deficient alkene here, so it can add to this carbon, and then subsequently this carbon can add back here. And you need to transfer an electron to close the cycle. And this way you can, in this case, it's not the 2+2 cycloaddition. In this case, it's down here as well. So you can either get the open one, but you can also form the 2+2 adduct shown here in order to do this type of chemistry. And again, what was realized is that if you have a proton source, so proton-coupled electron transfer, so if you get the proton here, then the reaction is not stopping after the first cycloaddition to make the 5-membered ring, but then it actually forms the 4-membered ring as well. So that's again a very interesting strategy, that a reaction very often you can, which is known by a non-radical pathway, that you can do the same reaction very often under milder conditions by bringing it to into a radical regime. And so again, this was done very nicely. The group of Yoon these days has been able to do these type of reactions in a very spectacular way by having an additional Lewis acid activation. You can see that they already had a Lewis acid here in their reaction as well, but now they're taking a chiral Lewis acid to make these reactions enantioselective. Okay, then we have another reaction. Here, let's look at this, again, the same idea. Should we run the reaction thermally, photochemically, or under radical reactions, which we might generate by a photoredox mechanism? And then, if you look at this cycloaddition here, this 2-methylbutadiene and this styrene, 4+2 cycloaddition, so Diels-Alder reaction. What's your feeling? Should this work? Oh, the answers cannot be seen because it's probably below. Okay, let me see. Okay. Okay. Okay, so sometimes it's good that I ask these questions, and it's good that you answer, but it's very interesting that the type of answer. No, it's not allowed according to the Woodward-Hoffmann rules. Really? Thermal Diels-Alder reaction? Of course it is, right? 4+2, cycloaddition, superfacial attack, so of course it is allowed. But the point is indeed, it's electronically mismatched, or you can also say the homo-lumo gap is too big, right? The one thing is that a reaction is allowed according to the Woodward-Hoffmann rule, so it can run concerted. But the other thing is if the homo-lumo gap is too big, if the homo and the lumo is too far away from each other, then the concerted pathway cannot take place. And this is the reason why usually we take an electron-rich diene and an electron-poor dienophile, or we do it the other way around. And this is the reason why, for example, a reaction like butadiene and ethylene, which would be the easiest Diels-Alder reaction you can think about, is not working. You need like 1,000 degrees and 200 bars, so it would work on Venus, but it doesn't work on the planet Earth, right? And so here we have another typical case. This is an electron-rich dienophile. The styrene, the butadiene, is an electron-rich diene, so that is electronically mismatched and would not work. But the group of Yoon showed again how you can make this work. And so very nicely, again, you do this under photochemical conditions with a ruthenium catalyst. And this ruthenium catalyst does not have the normal BIPI on this. It has a BIPI with electron withdrawing substituents, and these electron withdrawing substituents make that ruthenium catalyst an even better oxidant. And so this is a strongly oxidizing catalyst. And so what this is doing now is it can oxidize. Wait a minute, I'm on the wrong page here. It can oxidize this very electron-rich styrene. There's a paramethoxy group. This is really easy to oxidize. And one way you can draw this is you take an electron out of the aromatic ring, and now suddenly you have a styrene which is not electron-rich any longer. This is now electron-poor, right? It has become an electron cation. So this indeed now will readily react with the butadiene, and then in the very end it has to take back the electron from the catalyst. This closes the cycle, so you go here from ruthenium, you go from ruthenium 2 in the first step, you go to I just wonder if I oxidize this, I need to go to ruthenium 1. So we have again this reductive pathway. And then once this has reacted, the radical cation needs to give back, needs to take back the electron to go back from ruthenium 1 to ruthenium 2. And you see now suddenly the reaction works, room temperature, it works with fantastic yields in a fast way. So again, this idea that very often you can do an unprolonged reaction because the oxidation, of course, makes an electron-rich substrate, makes it to an electron-poor substrate. This is actually very good. What we should do now here is we need a 5-minute break, and we need to do two things, I think. The one thing I need to ask our technicians here, the people who helped me here so nicely with this. I can see that I'm not the only one who's cold here. I can see you guys are cold as well. And so I wonder if we can, other than that we can all run out in the sun now for 5 minutes, but if we can get this air conditioning a little bit down. I don't know. It's really, and I didn't bring anything, but I'm really cold, and I see you guys are cold too, right? So for me, this does not have to blast so much. And then, as I say, I would just recommend we do it because the tea break is only in an hour. So let's nevertheless have a 5-minute break, and then we meet here again in 5 minutes. Just even if you just go out and get warm. But I don't know. Can we turn